Okay, let's get this started. Welcome to the second What's New in the RDKit 2020-09 edition live stream. This is a big experiment. We haven't done these before today at least. This morning was absolutely terrifying to try doing this on YouTube via live stream because there's a bunch of different technology pieces that come together that have to work well in order for it to actually function. And things this morning actually seemed to go reasonably well. There were no massive technology problems. Hopefully that continues through this afternoon session as well. So some logistics on what we're going to do. You can see I'm going to do the presentation from a Jupyter notebook as I normally do. This session, this is normally something that I do at the UGM during the introductory pieces. And this year, because the UGM was virtual and for various technology reasons, I didn't end up getting a really long version of it. So I thought it'd be nice just to do this for people who wanted to connect to the live stream. And then at the end of this, I'll put the video up on YouTube so it's available for others. But I'm working from Jupyter here. The notebook itself is in GitHub. So here's the link. This link is also in the description box for the YouTube video. I'm assuming I remember to do that. And if not, I'll go back and do it when we're done here. The repo also includes a YAML file that has a Conda environment description, so you can actually create a Conda environment from that that'll install Python 3.8 and the RDKit and all of the requirements so that you can use this notebook. One thing that I noticed when creating an environment from YAML, uh, you need to configure Jupyter to be able to use the IPy side escape views. So you need to execute this command after you create the environment from the YAML file. If you just install widgets, if you just install the Python IPy side escape manually with Conda, you don't need to do this. If you have questions as we're doing this, please use the live chat box in the live stream. I'm going to try and keep an eye on this as we're going, and I'll answer questions. And then if you have feedback or suggestions about this whole experiment, whether or not it was useful, please do that with the mailing list or with the discourse group. And there's a link here to the discourse group. Obviously, you can put feedback in the chat as well. So let's go through. What I'm going to do is show some highlights, I guess, or important features from the most recent release, so from the 2020-09 release of the RDKit. I will also trickle in throughout a few things from the 03 release, so from the one earlier this year, because they feed into something that came in the most recent release, or just because I think it's important and maybe underappreciated. If you want the full list, of course, you can always go and look at the release notes, and that is comprehensive. It has everything that was added and all the bugs that were fixed. I'll start with just a very brief description of the 3 Google Summer of Code projects that we did this year. The first is not actually integrated in the RDKit itself, but it's a separate project that's part of the RDKit organization in GitHub. So Chris in that work did a integration that allows you to use the RDKit inside of MongoDB. So you can build a document store, store compounds in the document store, and do chemical searches with that. So substructure, exact structure, and similarity searches. It's quite nice. If you're a Mongo user, give it a try. The GitHub URL is there. In the RDKit core itself, there are some changes or some new features added by Shrey as part of his project. The first is a generalized file reader, and then the second is a multi-threaded multiplier. I have not included these in this presentation. They require a bit more description, and I'll be doing blog posts about those in the not too distant future. The generalized file reader just makes it easier to read files and molecules. You don't need to keep track of whether it's an SD file or a CSV file. You can just use the same command to create a supplier. And the multi-threaded multiplier allows you to create a multiplier that reads multiple molecules at the same time from a SDF file or CSV file. So that can, under some circumstances, end up with pretty dramatic speed ups in molecule parsing. The third project is something done by Manan Gol. That is an implementation of Ani and the RDKit. So Ani, for those who don't know it, this is a neural network force field that gives the force field implemented using a neural network that gives DFT quality geometries and energies for limited molecules involving a limited number of atoms or a limited subset of atom types. That contribution is not yet merged. The pull request on that is still open, and we're still going through it in order to finalize some details on that before it ends up getting merged in the RDKit core. But hopefully that'll make it into the 2021-03 release, so the next major release. There have been some improvements to the documentation that I think are worth mentioning. So the RDKit cookbook was completely rewritten as part of the 2020-03 release. That's a contribution from Ben Scalfani. This is really nice. It really improves the quality of the cookbook and makes it much more useful. It also introduces tests into the cookbook so that we now can detect when a code change breaks one of the recipes. There are also new sections of document added or to the documentation which document which pieces of CX Smiles the RDKit supports and which pieces of smarts the RDKit supports, along with all of the extensions that the RDKit has, because there's a number of extensions that we've added just to make smarts more useful or to make it easier to do really interesting queries. An important thing is that from a software quality and documentation quality perspective is starting in the last release cycle, we started running all of the documentation tests as part of our standard CI build in GitHub. So whenever you do, or whenever we do a GitHub commit or merge something onto master, we actually now test that the documentation doesn't break. So it's nice the documentation stays up to date. So now let's get into new features of the RDKit itself. I'm going to say something about the simplified JavaScript bindings a bit later after I've talked about Molddraw 2D. So I'm going to skip over this for the moment. Aside just to say quickly, in the release a year ago, so in 2019-09, we added some simplified RDKit JavaScript bindings to allow you to use pieces of the RDKit inside of web pages. So using them from JavaScript directly. The idea there is not to provide all of the functionality of the RDKit, but to provide a useful subset. And what's currently included in the useful subset is listed here. There's a demo page and some documentation that I'll show you in a bit. But now let's go on and look at the stuff that's available from Python, and I'll start working my way through this notebook. So go ahead and start. The first thing are some changes to ETK-DG, so to the RDKit's confirmation generator. As of the 03 release, ETK-DG v3 is available. So there's some improvements to the basic torsion terms there, but the big changes here is better support for better ring conformers and support for macro cycles. Serena and Shu did a paper which is linked here that describes those changes and how they were validated. I'm going to talk here in this stream. I'm just going to talk about the ring conformers or show you the ring conformer changes. If you want more information about the macro cycles, take a look at Shuje's entry in the cookbook, which is linked here. So let's take a look at what ETK-DG v3 does. So I'm going to start here by constructing a molecule. This is a molecule with a 6 ring. I build it from smiles, add hydrogens to it before generating conformations. I'm going to construct initially, for the first thing I show you, ETK-DG v2 conformers. I give it a random seed, so this is reproducible, and then I embed the molecule. So I just give that the molecule in my parameters object. And then in Jupyter, if I have the 3D Python extensions installed, and I, within Jupyter, set this IPython console, IPy3D equals true, when I display a molecule or when I just end a cell with a molecule that has a 3D conformer, it uses 3D to show you the molecule instead of showing it in 2D. So that's nice. If you have conformers, you can actually look at it. And what you will see for the 6 ring, the conformation that we get is kind of a twist boat form. It's not a nice standard 6 ring conformation. And this has been fairly typical of RDKit conformations for the past few releases. ETK-DG ETKDGV3, on the other hand, adds a new parameter, which is this use small ring torsions. If we do that and embed the molecule, we now, you can see, get a nice chair form of the ring. And almost all conformations you generate using these parameters will give you nice ring conformations instead of the weird hybrid conformations that you were getting before. And if you don't like this, if you want to get weird conformations or that they're useful to you for some reason, it's very easy to do that. There was a question from Omar about how good ANI is compared to MMFF94. That's really comparing apples to oranges. ANI is built parameterized from DFT data, and it supports a very limited number of atom types. I would encourage you just to look at the papers. They have a lot of validation data in there. Okay, back to the presentation. So the scaffold network implementation. This is also something that was added for the release earlier this year. We did an application note on this. So this was an application note I did together with Nick Stiefel and Francisca Navarez. There's a new module, RDKit Scaffold Network. I'll demo that using kind of a standard scaffold network set of demo compounds, which is these 4 antibiotics. I'm going to, instead of showing you text, I'm going to use graphical visualization of the network, and I'm going to do that using IPy Cytoscape and Network X. The code to do that is reasonably complicated. You can see it here, but there is a blog post, an RDKit blog post that has this code. You also have the notebook, so you can use it. I've adapted it slightly for this demo here. It's important to give credit. The person who originally figured out how to do this was Penn on the Iwatabi Penn blog. So this is where I got the idea from, or the original bits. I adapted that to work with the new code, and that's what we're seeing here. But when I do that, I can show the scaffolds for the set of molecules, and instead of, well, basically I get a nice network layout with the molecules and their scaffolds. Because when I do this for multiple molecules, it gets rather confusing. I built a bit of interactivity into the oops, sorry, this is the problem with the Jupyter Notebook. You have to be sure to re-execute the cells. Okay, I built some interactivity into the notebook so that I can show one molecule at a time and we can see what the parameters do. So here, let's pick the second one. You can see this is the default parameters for the scaffold network. You can see I have the molecule itself. In the first step of building the network, the side chains are pruned off of that, leaving this scaffold possibility. And then in the next step, this is fragmented to give these 2 scaffold possibilities. By default, when you fragment a scaffold into pieces, the attachment points are left on. You can see the stars here for the attachment points. If I want, I can turn that off, so I can tell it to only do scaffolds without attachment points. You can see now I have the scaffolds themselves without the attachment points indicated. There's also the ability to include generic scaffolds. So let me go back to with attachments and I'll turn on generic scaffolds. What happens here is after each scaffold is generated, there's another layer is added to the graph where all of the atoms in the scaffold are replaced with dummy atoms. So this is useful if you have scaffolds in your data set that include things like nitrogen walks, where they walk a heteroatom around the ring. Here you can you'll get a generic scaffold that allows you to link those molecules or those potential scaffolds that go through the nitrogen walk. You can see each of the scaffolds here has its generic form added. If you really want to go generic, you can also do generic bond scaffolds, which adds yet another layer to the network where all of the bonds have been replaced with single bonds. So now we're really just down to a framework, nothing like a scaffold anymore. You can play with this yourself when you download the notebook and really get a sense of what the parameters are and what they do. So that's why I find doing this in Jupyter, it's a really useful way to be able to explore parameters and their impact on the results for things like basically for anything where there's a complicated set of parameters. And in Jupyter with its interactivity pieces makes it super easy to do that. Next one is kind of a simple piece that is primarily intended for people, or primarily useful for people who are doing machine learning and who want to do data augmentation. So it's pretty common that the folks training neural networks want to have smiles for a molecule come in and have multiple versions of the smiles for the same molecule. And what people have done in the past for this is they've turned off canonical smiles and then generated smiles rooted from each of the atoms in the molecule. And that gives you some set of smiles for the molecule, but you don't really get random smiles. So we added some capabilities to get truly random smiles, which is this mold a random smiles vect function. You can tell it, you give it a molecule and tell it how many random smiles you want, and you get a vector of that many smiles. These are truly random, so it picks a random starting atom for each generation, and then each time it comes to a branch point, it picks a random atom to go to next, instead of using the rules that are normally used in the RDKit smiles generation. Of course, it's random, so by default, the results are not reproducible. So if I call this twice on the same molecule, I get different results, but I can provide a random number seed and get reproducible results. As you can see here, I do the same random number seed twice, and I get the same results twice. Okay. Next, a bit of a change of gears. This is improvement of chirality handling and reactions. In past releases, there has been some handling of, how to phrase this. The reactions did do something with chirality, and as long as you set the reactions up carefully, they would do the right thing. But it was pretty easy to screw it up, or it's pretty easy for you to do something correct that the RDKit would then screw up. And spent a fair amount of time in the last release cycle fixing those problems. So here's an example. This is a case where things were incorrect previously. So what I have is a reaction. You can look what I do is I have a carbon, central carbon that has three neighbors, a carbon, a fluorine, and a bromine. In this reaction, I'm doing alchemy and turning the bromine into a sulfur. And I'm also reordering the bromine and the fluorine around the carbon on the right-hand side. So first it was in the reactants, it was fluorine and then bromine, and then the products, it's sulfur, which was the bromine, and then the fluorine. And when I do that, I also flip the chirality. So I flip the stereochemistry from at to at, because I've changed the order of two outputs and changed at to at. This has the effect of leaving the stereochemistry the same. So it's flipping, but then it's flipping again. So we expect to get the same results. And in fact, we do get that. So if I construct a molecule, the molecule shown here, and then get the smiles after I run that through the reaction, you can see that I get a molecule that has the same chirality as what I went in with. So it's carbon and then fluorine sulfur. Previously it was fluorine bromine, and it's still at, which is what we expect. I'm not going to go through them in detail in this level of detail, but there's two other examples in the notebook showing that we can now correctly add a neighbor to a chiral atom and correctly remove an atom from a chiral atom and have this all work properly. Another reaction-related feature or relevant to reactions is deprotections. This was work done by Brian and Joanne at Relay. And what they added is it's pretty simple, but incredibly useful. So there's a new module called RDDeprotect. You can take this and you call the deprotect function, you give it a molecule, and it removes protecting groups from that molecule and gives you a molecule with the protecting groups removed. So here's an example. I have, this is the molecule I started with, and you can see it has a TMS protecting group on this oxygen, and has a Bach on this nitrogen. After I call the deprotection function, both of those have been removed. The molecule also has a property added to it, which is deprotections, and that includes the names of the deprotections that were applied. So here you can see that we removed a TMS and a MOC, which you can also see from looking at the structures. In case you're me and you can never remember the names of the protecting groups, this is a nice way to dig that out and find out what was applied. There is a standard library of protecting groups that are included. You can get that by calling the getProtections function and then just printing them out. You can see we have a number of them for alcohols and amines, and then one at the end for carbonyls, for acetyl ketol carbonyls. These are what are tried by default. You can add your own deprotections if you want to, but this is what's in the default list. I assume that this list will grow with future releases as we have new protecting groups come in and as we have people contribute new protecting groups. If I don't want to apply all of these, I can choose to only do particular ones. So in the example here, I'm going through all of the deprotecting groups and I'm selecting only the ones that apply to amines. So I'm doing a list comprehension where I go over all the protecting groups, and I'm only picking out the ones where the deprotection class member is equal to amine. I collect that in the only amines list, and this time when I call deprotect, I pass only amines as an argument to deprotect, and you can see here now it has left the TMS on the alcohol, but it's removed the BOC from the amine. So you do have control over which groups you deprotect if you want to do that. That's deprotections. Next is a block of improvements around the molecule rendering. This includes features that were added in both the 03 release and the 09 release. This is functionality added. The majority of this was added by Dave Cosgrove in some work that was funded initially by MedChemica, and then I funded some of it. I also did some of the work that you'll see. But there's been a dramatic improvement in the quality of the rendering, and we've also had some pretty sizable changes or added some additional interesting new options to the rendering. This is the molecule I'm going to use as my example. It's a bogus molecule, but it shows it has a number of things that I want to demonstrate. The first is there's a dummy atom in it, which is the question mark. The other is I'm constructing this from a CX smiles, and the molecule includes information about stereochemistry, or enhanced stereo at the end. So there's an and group in here. You don't see those by default in Jupyter. You can tell Jupyter to do that, but it's by default, you don't see it. Now I'm going to do another one of these interaction things where I can set the various options for the rendering, and then the rendering here will be updated. So we can start by doing some basic things. So I can turn on atom indices, and you can see that those show up. It used to be more difficult to do this. I can turn on bond indices, and you can see the bond labels or the indices of the bonds. This is useful information if you're trying to track down. These tend to be most interesting or useful when you're trying to track down problems or the molecule's not behaving as you expect it to do. We can also turn on stereo annotations. So in this case, this chiral center is S stereo, so you can see it's labeled S. Here are the two and atoms from that enhanced stereo group, and you can see the double bond is labeled E. So when you turn this on, any stereo features that the RDKit recognizes will be labeled in the output. One thing I forgot to mention that is definitely worth mentioning is one of the big changes is that we can now, let me zoom out so it's a bit easier to see. The rendering across the SVG render and the PNG render is now more or less the same. So if I switch from SVG to PNG, if you look at the molecule rendering itself, you don't really see the difference. If you're if you stare at it closely, you can see that the PNG, the lines are anti-aliased, and in SVG, they're not as anti-aliased, but that's about the only difference you see. And this happened because uh, we managed to fix, or Dave managed to fix the font handling. So it used to be that we really had problems getting the font, handling the font so that atom labels showed up where they were supposed to show up. And to do that consistently across SVG and PNG was just impossible. But as part of the last release, Dave added free type support. And so now we get really good font handling, and you can see that the atoms labels don't move when I switch between SVG and PNG. It also looks a lot better. Some other things that we're showing. So if you like terminal methyls to be indicated, you can do that now. Um, this dummy atom I can also show as an attachment point, so it puts the squiggly line in if you're working with RGroups. And there's an option if you want to not have the colors, you can always just go black and white. And then of course we can change the font, the labels. So there's labels and you have control over the font size as well. So the notebook has all this in here. You can see how I'm changing those parameters and use this as a way to learn how to control the rendering and get a sense of the new features that are available. Another big piece that I'm really excited about is in the most recent release, we now store molecule metadata in PNGs so that when you generate a PNG from the RDKit, it includes information about the molecule itself in the PNG and the metadata there so that you can reconstruct a molecule from the PNG without having to do image processing. So here's an example of that. I'm going to use the Moldral 2D Cairo class. This is how I get PNGs if I just want to get the PNG text. So I create the object, I draw the molecule, do finish drawing, and then get drawing text. This PNG that I get back, or this string that I get back, is now the binary text that describes the PNG. And I can display that using Jupyter's image class. So image, and you give that the PNG, and it'll show it to you, as you can see here. What I can do and what's new is there's now this chem mol from PNG string function. I give that the PNG and it gives me back a molecule. And you can see that I have the right molecule. I can convert it to CX miles, which you see here. I have the molecule and the coordinates of all of the atoms, as well as information about the enhanced stereo. And I can also just draw the molecule, and you can see it's the same molecule we started with. So this is, I think, really nice. You can do the same thing with multiple molecules. So if you do draw molecules instead of draw molecule, you end up with the molecules in the PNG. And then there's a function, moles from PNG string, which gives you back the list of the molecules that were encoded in that string. So you can see them here. So I put the 4 antibiotics we were working with into the PNG, and I pull them back out here. This works for reactions as well. There's some demo here. And then the last bit that I think is useful and worth pointing out is we can also put metadata, so additional metadata in the PNG. So for example, if I want to put a molecule in and some data associated with that, like I would do in an SD file, I can do that. And all I have to do is construct a dictionary that has keys for values, strings for keys and values, and then call this add metadata to PNG string, where I give it the dictionary and the PNG string I want to add it to. That adds this metadata to the PNG, and then I can then get it back out with chem metadata from PNG string. And you can see here the keys that I get out are, I have yield, solvent, and catalyst, which I put in, and then these additional 2 keys are the molecular metadata that was added for the molecule itself. So I have a reaction pickle and a reaction smarts added to the PNG. For technical reasons, these results come back as byte objects, which is a detail that's just worth pointing out. So now, by default, if you generate a PNG from the RDKit, for example in Jupyter, you copy that out and paste it into a Word document. save that Word document, the metadata attached to the molecule is in the PNG in the Word document, and it does not get stripped out by Word. So we verified that Word leaves that intact. If you want to demonstrate that to yourself, what you have to do, it turns out there's no way in Word to get there's no way I've been able to figure out in Word to get the data out directly. So you have to unzip the Word file or unzip the PowerPoint file and then find the PNG in the zip file. But once you do that, you can see that the metadata stays intact. So it's really cool. Basically now when you put a molecule image in your documents, you can reconstruct the molecule later, which will eventually allow us to do substructure searching in PowerPoint documents, which I think is super cool. The last bit of rendering that I want to show, or the last bit of mold drawing code, is MoldDraw 2D.js. So to this point, we've had a renderer that targets SVG, and we've had a renderer that targets PNGs. Now we also have one that targets the HTML5 canvas. And I will just demonstrate that. This is part of the JavaScript bindings. You can't use this from inside of Python or from C++. It only works from inside the JavaScript bindings. So this is my demo page. This is linked from the slides or from the notebook itself. I apologize for how ugly this is. I am not a JavaScript programmer or an HTML person, so this is about the best that I can do in terms of making things not look like crap. But this is a demo of RDKit.js. I can edit the smiles and you can see the molecule changes. I can add smarts and it'll highlight the smarts on the molecule. You may have noticed as I was changing the molecule, the descriptors here, these computed values were also changing. You can see that this is an SVG, and down here is an HTML5 canvas. You can see that aside from being a different size, the results look the same. This is the same as with PNG and SVG. The things now really look exactly the same. And the demo page also includes the ability to play around with some of the parameters so you can see what shows up, what the options are, and what they do. There is another, because the JavaScript code really has very little or basically no documentation aside from this page. I created a new documentation page, which is this getting started in JS. HTML, this is also in GitHub, and the live version is here on rdkit.org. Again, it's linked from the notebook. What this has is some really simple examples of doing stuff with RDKit. With RDKit.js. So this first example constructs a molecule from smiles, calculates inchi key, canonical smiles, and the mole block. If I click run, it executes that. Again, this is all running in my browser, and you can see all those values for the molecule I just created. This one demonstrates calculating descriptors. You can see the descriptors that are calculated by MoldJS, RDKit.js. We can draw molecules. So this one is SVG. Here's one that uses the HTML5 canvas. All of these are editable, so if you want to play around with what's there and see how it changes things, you can do that easily. It also shows how to do the substructure searching and highlighting, control additional options and do things like set atom labels and legends, change highlight color, etc. There's documentation here that also shows what the options that are supported are and some additional functionality. So this is, if you want to start using the JavaScript bindings, this at the moment is the best documentation we have. It's not pretty, and I'm sure you'll find bugs in it. If you do, if you find bugs, please report them. If you can fix them, it'd be even better. And if you figure out a way to make this look better, please make it look better. As I said, I'm not good at doing nice looking HTML. So if you improve it, please submit a pull request. It would be great to have these actually look good. Okay, one last bit to show for the drawing code is a somewhat extreme example of what is now possible. This is from a blog post I did recently. showing what you can do with the new code. So what you're seeing here is a set of molecules that had CDK2 inhibition data, or I think that's actually binding data, measured in Kemble. They all show the same scaffold, and what I did is I did an R group decomposition based on that scaffold. I oriented all of the molecules so the scaffold is consistently oriented, and then I colored the R groups based on their R group. This R group down at the bottom is always blue, and the one at the left is always green, etc. And this is stuff that you could not have done previously in the RDKit, and if you tried to approximate it, it wouldn't have looked as good. So this is just shows a nice possibility of the kind of things you can do. This particular visualization was inspired by a conversation at the UGM, actually, based on some of the work that Dominique Seidel at the Charité was doing on kinase ligands. I thought this would be a nice way to explore visualizing her results. Next bit to look at is abbreviations. This is also code that was sponsored by Nick at Novartis. What we're going to do here is start with a molecule. This molecule has two groups on it that has this methoxy and this carboxy. The abbreviations code allows you, basically it edits the molecule or gives you a new molecule back where the methoxy is removed and is replaced by an abbreviation, and the carboxy is removed and replaced by an abbreviation. It's quite simple. What we can do with this, so it's simple, but it leads to cleaner drawings sometimes if you want to do that. By default, this will not apply abbreviations that cover more than 40% of the molecule. So you can see down here at the bottom, this molecule with a CF3. CF3 is a recognized abbreviation, but because that CF3, those 4 atoms are more than 40% of the molecule, the default behavior of condensed mol abbreviations is just to leave it intact. I can provide a max coverage argument where I provide the fraction of the molecule that I want to allow the thing to cover. So that's shown here. And so then this last molecule where I allow the abbreviation to cover up to 80% of the molecule, then the CF3 actually gets condensed. The abbreviations that are available is there's a default set, which you get from this get default abbreviations. It is pretty easy to add your own abbreviations. So we just have a number of common functional groups that are recognized by default. You can also, if you want to write the abbreviation data back out, you can annotate the abbreviation as an S group on the molecule, and this is with label mol abbreviations. So here I give the molecule, again, the list of abbreviations I want to look for, and optionally max coverage. And you can see what this does here. I have the molecule up at the top. This is, well, let's just look at what the molecule looks like. This is just 2 carbons, and then so it's a carbon with a trifluoro methyl group attached to it. So very simple. You can see the output mol file has all 5 atoms in it, but it also has this S group that says that 4 of those atoms are involved in an abbreviation. So if you read this mol block into Marvin Sketch or something like BioViaDraw or ChemDraw, they will either show it with the CF3, this actually abbreviated to CF3, or they'll offer the option to collapse it down. Once I have that, I can then condense. If I want to render it in the RDKit with the condensed version, I can just say, I can read a molecule in that has those abbreviation S groups, call condense abbreviation substance groups. It gives me a new molecule that has the collapsed abbreviations. So if I have a molecule that I want to do abbreviations on, that's condensed mol abbreviations. If I actually want to modify the molecule itself, label mol abbreviations if I want to get into the S groups. If I read S groups in, if I read a molecule that has S groups in with abbreviations, I can condense those with condense abbreviation substance groups. Okay, some words about the CoordGen integration for people who don't know it. The integration with CoordGen, which is a very good 2D coordinate generator for molecules developed at Schrodinger. This was added a couple of years ago, actually. It's been in the RDKit, but it's not been a default, and it's still not a default, and we'll talk about why here. So let's start with looking at these molecules. So I read in the RD CoordGen package, that's where this is, or I can, in RD Depictor, which is the RDKit's code that does 2D coordinate generation, I can also have it call out to CoordGen. I'll start by showing cyclosporin the way the RDKit normally does it. So this is the RDKit's depictor, and it takes, for macro cycles, it takes the strategy of, well, I don't really know what to do with this, so I'm just going to draw a big ring, because at least there you'll be able to see everything. Obviously, that's not optimal. Chemists don't really like things like this, but at least you can see everything, right? I can use CoordGen to do that, and you can see it does a much better job of drawing cyclosporin. It actually looks like a macrocycle. And that's why you would want to use CoordGen. The problem is, and this is the reason that CoordGen is not the default, CoordGen does a lot of work in order to do this, and it makes the rendering take longer. For some molecules, it takes the rendering can take seconds with default parameters. Whereas the RDKit rendering never takes anything like that long. It takes at most a tenth of a second for a molecule, maybe a couple tenths of a second. So the first thing that changed for this release is we changed the default precision that CoordGen uses when cleaning up coordinates. And that has the effect, you can see it here for cyclosporin, it has the effect of taking the runtime from 133, this is what, from 133 milliseconds, this is the CoordGen default parameters, to 80 milliseconds. And this is the RDKit's new default parameters for CoordGen. So with cyclosporin, it really helps. It takes like 50% less time. Well, not 50% less, but it takes about 2/3 of the time to generate coordinates for cyclosporin. And if you go through the notebook, you can see it doesn't make a huge difference or much difference at all in terms of the coordinates. This molecule is a more extreme example. Again, the RDKit doesn't do a great job with the macrocycles. If I use CoordGen with the default parameters, it takes 133 milliseconds, which is a chunk of time, right? That's a tenth of a second is a while to wait for coordinates to come back. The RDKit doesn't take anything like that long with this molecule, but you can see you get a much better confirmation. The default parameters with CoordGen, so using its standard precision, we do get a somewhat better rendering, and I can't show them both to you at the same time because it just doesn't work. There's not enough screen space, but it is somewhat better, but it takes a lot longer. So 660 seconds. It takes almost 2/3 of or it takes 2/3 of a second to generate this confirmation, this 2D confirmation. So take home, it's now faster to use CoordGen than it was before, and that's because we changed the precision settings, and it's also the guys at Schrodinger have done a lot of work on optimizing that, optimizing the code. So CoordGen itself is also faster. So it's now faster than it was before. I think it's actually a viable thing to use almost all the time, but we haven't made it the default yet. We'll see. Maybe for the next release, we'll make it the default because the confirmations, as you can see, the coordinates really are a lot better than what the RDKit itself does. The same thing is true if you do natural products. The output you get from CoordGen is a lot better than what the RDKit does. Okay, I'll skip over this one. This is a little bit of cleanup that you can do, some 2D cleanup with CoordGen. And I want to talk a little bit about tautomers. The RDKit has had support for doing tautomer enumeration for a couple of years now. It was added by Susan Lung as part of her Google Summer of Code project where she integrated MolVS. We did not, however, expose the tautomer enumeration to Python, so you really couldn't get there from Python, which means most people didn't use it. For the 2020 03 release, we did expose it to Python. So you can now, in RDMol standardize, which is where our MolVS is in the RDKit, or our implementation of MolVS, our port, there's now a tautomer enumerator object. This is the molecule I'm going to use as my example. And I can tell the tautomer enumerate to enumerate the tautomers of that. And you can see these are the 4 tautomers that it finds. I can also have the code give me a canonical tautomer for the molecule. And you can see this is the canonical tautomer. I just say, I give it the molecule and have the tautomer enumerator canonicalize it. The notebook has a disclaimer or caveat about the canonical tautomer taken from the documentation. I'm going to repeat it, even though you can read it yourself, because it is super important. This is a canonical tautomer. This is not intended to be the most stable tautomer in any particular solvent or any particular conditions. So the intention is if I give you the molecule in some other tautomeric form, you'll get this result. If I reorder the atoms, you'll get this result. We tried to add a scoring function that gives you tautomers that don't look horrible. Right, so unlike Anchi, where if you look at those tautomers, they really look ugly, we've tried to have it not be too terrible looking, but if you look at these enough, you're guaranteed to find something you won't like. That's not a bug, right? We're not trying to produce the most stable tautomer. We're just trying to produce something that's canonical, and it'd be nice if it also looked okay. So the way we do canonicalization is we score the tautomers, and that scoring function is available from Python. So here I loop over the tautomers and I score each one, and I've now shown the 4 tautomers with their scores. And you can see the highest scoring one, the one over here, is the one we got as the canonical tautomer. Okay, so that's that. That's enumerating tautomers and getting the canonical one. Another thing that was added, this is for the most recent release, the 09 release. This is work done by Gareth Jones, funded by Schrodinger, is we added the ability to do tautomer insensitive searching. So specifically what we're doing is doing a substructure search that matches all of the tautomers of the query structure. So I'm going to use the same molecule I was using above in the same tautomer that I was using it above. And I'm going to search in doravirine, which is shown here. You can see by default, doravirine does not have this molecule as a substructure, and that's because the ring that I've drawn is in a different tautomer from what you find in doravirine. However, with the new code, I can construct this tautomer query object, and then I can ask that tautomer query object if it is a substructure of doravirine, and you can see that it is. I can ask the object to give me the matches or the atoms matching in doravirine, which you can then use for highlighting. I apologize, I haven't done that here in this notebook. And I can also have the searcher give me back the actual tautomer that matched the molecule. So in this case, this is the tautomer of my query that matched the molecule, that matched doravirine. The tautomer query itself, this tautomer query object, has a additional method, getTemplateMolecule, which returns to you the molecule that's actually being used for the search. And so this is a molecule where most of the bonds have been converted, the tautomeric bonds have all been converted to queries. It's difficult to depict this, so I'm just showing you the smarts. But what you can see is that the bonds in the ring have all been converted to single or double or aromatic, and the bonds out to the outside of the ring as well, the bonds out to the oxygen atom are also marked single, double, or aromatic. So basically any bond that's involved in tautomerism has been marked as being single, double, or aromatic. That's how this works. Super important reminder, the search is looking for tautomers of the query, not of the molecule you're searching in. So it's the query tautomers, not the database molecule tautomers. This will confuse you, so people definitely get confused. This is an example that John Mayfield raised during the UGM. Here's a molecule that I'm going to use as a query. And these are 2 molecules that are tautomers of each other. This is a tautomer of, there are tautomers of this that match tautomers of this, but there are no tautomers of this that match either of these molecules. And this is the results that you see. So again, if you're doing the tautomer insensitive searching, it is insensitive with respect to tautomers of the query. If you want to search additional tautomers in the database, so for the molecules you're searching through, you need to do tautomer enumeration on those. I'm not going to discuss it here due to time constraints, but there's also the pattern fingerprints that we use to screen out substructure searches have been extended to support tautomer insensitive searches. And so it allows you to do these tautomer insensitive search patterns in an efficient way. Okay, next bit are some changes to adjust query properties. Adjust query properties is essentially, it's a block of code that the most useful, you can do a bunch of things with it, but what it's really intended to do is to take a query molecule or a sketched molecule and get it ready to be used as a substructure query. It has a lot of functionality, and this notebook demonstrates a lot of it. I'm not going to go through all of it here because it's just too much. I will do a blog post on this in the not too distant future, so in the next few weeks, that kind of goes through the examples that are here in detail and describes a little bit more about the thinking behind it. But you have the notebook if you want to see what's there. And you can see there's a fair amount of information that's in the notebook, including, actually, I find this visualization of query in the column and molecules in the rows and whether or not it matches quite useful. So if you want to learn how to do that in Jupyter, that's in this notebook. Okay, I'm going to scroll down though, because we're not going to talk about this here. The next piece to talk about is the mole enumerator. This allows you to take queries that are drawn in mole files that include things like position variation bonds and link atoms, and enumerate those so that you get all of the molecules encoded by the query. So a specific example for position variation bonds. This is a molecule with a position variation bond. I apologize, the RDKit at the moment is not capable of showing that to you. But basically what this mole block says is this methoxy is connected to any of these three atoms. So it's here or here or here. That is not, by itself, that's not particularly useful in the RDKit. The information is there, you can read it in and write it back out again, but you can't really do anything with it. But now with the RD mole enumerator, you actually can do something. So I can construct a mole enumerator object. I can say I want to enumerate position variations. I can apply that to this molecule, and it spits out these three molecules. Those look like hell because it hasn't regenerated the coordinates. So let's regenerate the coordinates. And now you can see here I have the three molecules that were encoded there. So what this returns to me is a mole bundle that has these three molecules in it. So again, position variation, the methoxy is attached here, here, or here. Here are the molecules in the mole bundle. The methoxy is attached either ortho, meta, or para. The other thing that you can currently enumerate are link nodes. Again, I apologize that the RDKit cannot currently show you the link node, but this is a molecule that has a link node here. So this carbon connected to an OH is present in this molecule 1, 2, 3, or 4 times. And here is how you do that enumeration using the mole enumerate. So I just say I want to enumerate a link node, I give it the molecule, and again, it gives me back a mole bundle that has those 4 molecules in it. It's worth explaining what the mole bundle is for. So when we do the enumeration, it gives us back this mole bundle. This is a collection of molecules. As you can see, I can get the individual molecules out by treating the bundle like a list, but I can also do querying just with the bundle itself. So I can ask the bundle if it has a substructure match to a particular molecule. I can ask a particular molecule if it has a substructure match to the bundle. So bundle has substructure match to the molecule means any of the molecules in the bundle match the molecule, match the query. Using the bundle as a query is any of the molecules in the bundle, when treated as a query, are substructures of this molecule. So the bundle can be used either as a query or as a set of things to query. And there's a number of other places in the RDKit that give you back mul bundles. This is not new functionality. It's been there for a while. Okay, we are now running low on time, so I'm going to skip over the enhanced stereo and substructure search changes. Again, this is documented here. This is also documented in the main documentation that explains how this enhanced stereo actually interacts with substructure searches. The last bit I'm going to show, let's see, make sure that this is actually the last bit I'll show. Yeah, so the last bit I'll show is a bit more around the new stereo code. So there was a presentation at the UGM that I did together with Ricardo from Schrodinger, detailing what the new stereo code, some new stereo code that's available in the RDKit. And this is two pieces. It's new code that's better at finding potential stereocenters and molecules, and it's also code that's much better at labeling, applying SIP labels to molecules. So if you've tried it in the past with the RDKit, the SIP labels that you get with the RDKit by default are only approximate, and sometimes they're extremely approximate. This new code is much, much better than that. This is based upon some code that it's a C++ port of some code that John Mayfield wrote in Java, and there's a paper, not an RDKit paper, but there's a paper that John was on describing how the code actually works. It turns out the SIP rules are really, really, really complicated. The demo here is basically just going through and showing how some of the new code to find molecule stereocenters works and how it's different from what we had before. I'm going to skip over a lot of that. I will show some of the things that are different. So for example, this molecule here, using the new labeling code, the atom in the middle is properly labeled with small s. Previously, this would have had a large s assigned, but it should be small s. I have an extreme example because I really enjoy this molecule. This is something that Salome Reeder at the ETH shared with me. I really like this one because this is super dependent stereochemistry. Like this is a stereocenter, potential stereocenter, because these two are each potential stereocenters. These two are each potential stereocenters because these are potential stereo bonds. And as long as everything is specified on the edges, then and sufficiently different from each other, then the atom in the middle ends up being an actual stereocenter. Here's an enumeration showing that and labeling things. Okay, the last one I'll just show an example of the SIP labels, the new correct SIP labels. This is the previous version of the RDKit. It's still the new version. The new code is not used by default. These are the old inaccurate SIP labels. This particular molecule is labeled R previously, and it is actually S. Also a demonstration that we now properly do ring stereochemistry. And I'm going to skip over this last bit because we're more or less out of time. I wanted to break this at an hour. This code, the notebook is in Jupyter, in GitHub. The links for this are in the description of the GitHub video. What's going to happen when I shut this down at some point, I don't know how long this takes. The one from this morning still isn't done, but at some point, YouTube is going to allow me to crop out the beginning and end of this. I'll then share this as a video on YouTube, so it's available for later. I'll also then share that more broadly. But in the meantime, feel free to check out the code that's in GitHub, or check out the video and the notebook in GitHub. Again, if you have questions, if you have any now, you can pop them in a live chat. I'll hang around for another minute or two. But otherwise, please put them to the mailing list or to our discourse group. So I will hang out for a little bit to see if there are any questions come up in a live chat. But otherwise, thank you for paying attention. Thank you for attending. I hope this was useful. As I said, this is an experiment. If I get sufficient feedback that this was useful, then I'll do it again for the next release. Otherwise, I'll just cancel it because it is some work to get this put together. Again, thank you and bye-bye.